Ever wonder why the Earth looks different on different maps? Why sometimes Greenland looks bigger than Africa? Or why Australia looks like it could fit neatly inside the United States? That's because of geographic coordinate systems. Today, we'll talk about the two big types: geographic coordinate systems, or GCS, and projected coordinate systems, or PCS. By the end of this video, you'll understand what each does, how they differ, and why it matters when you're working with a geographic information system. A quick caveat: this isn't a step-by-step tutorial. I'll use Google Earth and ArcGIS Pro to show a few examples, but only to highlight key concepts. My goal here is to explain why coordinate systems are important for any GIS student or analyst to know about, not to walk you through every button or menu. If you're looking for a full tutorial on how to define or switch coordinate systems, I'll link to one in the description. A coordinate system is just a framework for describing where something is on the Earth. There are two families: geographic coordinate systems based on latitude and longitude, or just XY, and projected coordinate systems, which flatten the Earth into a map with distance units like meters or feet. Think of it like this: a GCS is like a globe, while a PCS is like a flat map pinned to your wall. One preserves Earth roundness, the other flattens it out so we can measure and analyze it. But flattening comes with trade-offs. The big advantage of a geographic coordinate system is that it accurately pins locations on the Earth's surface. But there's a catch: degrees aren't fully consistent for distance or area. 1 degree of longitude in Philadelphia isn't the same as 1 degree in Mexico City, because longitude lines converge as you move toward the poles. Let me show you what that looks like in Google Earth. Here we are in Philadelphia. I'm using the ruler tool to measure the east-west distance between two longitude lines. You can see it comes out to just over 4 kilometers. Now, let's float south to Mexico City and do the same thing. Here, between the same type of longitude lines, the distance is closer to 5.5 kilometers. The difference shows how longitude spacing depends on latitude: wider near the equator, narrower as you move north or south. This is where projected coordinate systems are useful. A PCS mathematically transforms Earth's curved surface onto a flat map, letting us use standard measurement units like meters or feet. But here's the key: no projection is perfect. How you flatten the Earth changes the way distortion shows up. Let's look at 3 common types of projected coordinate systems. In this illustration, you see a globe wrapped in a transparent cylinder touching along the equator. The Earth's grid projects outward, and when the cylinder is rolled up, it becomes a rectangle. This is how the Mercator projection works. It preserves shapes pretty well near the equator, but areas stretch badly toward the poles. This is why Greenland looks enormous. It's great for navigation because straight lines on the map match compass bearings. Now look at the cone. Here the cone touches the Earth along a line of latitude. When unrolled, the map becomes fan-shaped. Latitude lines appear as arcs, and longitude lines radiate like spokes. These are ideal for mid-latitude regions like the US or Europe. Distortion is minimized along the standard parallels where the cone touches the globe. That's why state and regional maps often use conic projections. Finally, the azimuthal projection. In this picture, a flat plane touches the globe along one point, here the North Pole. The Earth's grid projects downward, creating a circular map. Latitude lines form concentric circles, longitude lines radiate outward. This type of projection preserves direction and distance best from the center point outward. That's why it's often used for polar maps, airline route maps, or when you need to show direction from a single place. So why should you care? Because your results depend on it. Let's say you want to calculate crime densities around police stations. Let me take you into ArcGIS Pro to illustrate this. The police stations are mapped as little badges. You create 1,200-foot buffers around each station. By default, though, the buffer tool uses the WGS 1984 Geographic Coordinate System. That's fine for GPS, but not for GIS analysis. Why? Because when you open the attribute table, the shape length and shape area fields are in degrees, map units that don't translate into real measurements like feet or square feet. To fix this, you use the Project tool to create a new layer in a projected coordinate system. Since I'm working with Philadelphia data, I chose NAD 1983 State Plane, Pennsylvania South. Its linear unit is U.S. survey feet. So now, when I open the Properties tab and examine the data source and spatial reference, I'll see that I now have a projected coordinate system measuring distance in U.S. survey feet. And in the attribute table, the shape length and shape area fields are now expressed in feet and square feet. With that, you can meaningfully calculate crimes and other events per unit area. State plane systems are especially useful for local governments, police departments, and analysts working with city data because they minimize distortion within that region. So when you're working on something like crime hotspots, buffers, or land use analysis, state plane is usually your best bet. Okay, let's recap. A geographic coordinate system uses latitude and longitude in degrees, great for locating positions on the Earth. A projected coordinate system flattens the globe so that we can measure distance in standard units like meters or feet, great for analysis. Cylindrical, conical, and azimuthal projections each flatten the Earth differently, with their own strengths and weaknesses. So when you're working locally in the US, the state plane system is often the most precise projection you can choose. So remember, no projection is perfect, but the right one makes your analysis meaningful. Thanks for watching, and I'll see you in the next tutorial.